right, thank you for the opportunity to share some of my research with you today. My name is Connor Bishak, and I'm a Washington Research Foundation postdoctoral fellow at the University of Washington in David Ginger's group. And I'm excited to announce that I'm going to be starting at the University of Utah in the chemistry department in the fall of 2021. And today I'm going to be sharing some of my postdoctoral work on structural transformations in conjugated polymers upon electrochemical doping from aqueous electrolytes. And so so that we're all on the same page, the types of materials that I'm going to be talking about today are called organic mixed ionic electronic conductors. These are typically conjugated polymers that have side chains that enable ion transport, like these ethylene glycol-based side chains here, and a conjugated backbone that enables electronic transport, like this polythiophene here. And because these materials have this dual transport property, so they can transport both ions and electrons, they have really interesting properties that are useful for a number of different technologies. So some examples of those technologies are organic electrochemical transistors. These are really important devices for bioelectronics that allow you to convert ionic signals to electronic signals and vice versa. These are also really promising for charge storage applications, particularly when you really need fast charging and discharging times. They're also important for neuromorphic computing and thermoelectric applications. And so all of these technologies rely on this process that we call electrochemical doping. And so what happens in this process is if we put our system in a typical electrochemical cell, so we have an electrode down here in our reference and our counter electrodes in this liquid electrolyte solution, if we apply a bias, we inject a hole or an electron into this polycrystalline conjugated polymer film, and that causes an ion to enter the film and bind to this charge to create charge neutrality. And what it creates is what we call a polaron-ion pair, and this changes its local environment and also causes the conjugated polymer to become conductive so that electrons can migrate through the material. If we apply a reverse bias, then these ions come out, so this process is reversible, and we can cycle this a number of times. And so in the bulk level, what this looks like is, since we're changing the electronic properties, these materials are electrochromic, so they start off as this kind of pink color, and then when we drive ions in electrochemically, it becomes more gray. And so typically, conjugated polymers have these alkyl side chains, which are good for things like solar cells or field effect transistors. But these alkyl side chains are really terrible at transporting ions, particularly biologically relevant ions. And so there have been a number of groups recently that have made modifications to these types of polymers to switch these alkyl side chains with ethylene glycol-based side chains. And in this paper by Alex Giovannotti and Jonathan Rivnay and others, what this shows is that when you have these glycolylated side chains, ions can enter the bulk of your polymeric material. We've also showed that these glycolylated side chains can influence the kinetics of ion injection. So this one polymer P3-MEMT is much faster than the alkyl version P3HT. So the types of the materials that I'm going to be talking about today are this P3-MEMT and this PB2T-TEG. So these are two polymers that have very similar structures. So you can see they both have kind of a polythiophene backbone, but the PB2T-TEG has this phenylene group, and they both have these ethylene glycol-based side chains. And the types of questions that we're really interested in answering are: how does ion insertion impact polymer structure? We know that this ion takes up volume, so it really needs to displace some of the polymer when it enters and binds to this hole. And this also changes the local electronic properties, which can have an influence on the polymer structure. And then once this is formed, how does this polaron-ion pair move within the material? And so we're using P3-MEMT and PB2T-TEG as two systems to look at these effects. And what we discover, this is kind of a spoiler, is that when we inject ions into P3-MeEMT, we see very minimal structural changes. Yet when we inject ions into Pb2-TTEG, we actually see a structural phase transition happen in this material. And this is really the first structural phase transition that's been seen upon ion injection into a conjugated polymer. And so to investigate first how this polar-on-ion pair moves within the material, we do what we thought was a really simple experiment. So we electrochemically doped one side of the sample, so there's ions or polar-on-ion pairs on the left, and no ions on the right. And then what we wanted to do is watch this interface between an ion-rich and an ion-poor region relax to equilibrium. And so what we expected to happen is that this would follow Fick's second law. And so what we would see, as shown in this little simulation down here, is a blurring out of this interface as ions are moving from left to right, and the absence of ions is moving from right to left. And so if we do this experiment, and now we're looking just with an optical transmission microscope, what we see here is that with P3-MeEMT, this behaves basically like we expected. So we see this blurring out of the interface. Whereas with Pb2-TTEG, this interface actually remains sharp and still migrates. And we can perform calculations to reproduce this. So this looks very much like what we would expect from Fickian diffusion. And this looks a lot like what we would expect if there was restricted diffusion at the interface. I'm not going to go into this in detail, but we can also zoom in on this interface and using nanoscale infrared imaging show that it's still really sharp even at the nanoscale. So looking at both the signature of the ion and the topography simultaneously. So to figure out what was going on here, we decided to turn to X-ray diffraction. And so before I talk about our results, I just want to say what is typical of conjugated polymers. So typically conjugated polymers expand continuously with ion insertion. And so this is a really nice study by the Siegelman and Chabanet groups, where they showed that as they inject ions into P3HT, they see a continuous expansion of the lamellar spacing. And what that means is that there are ions being injected between these two strands, kind of where the side chains are, and that leads to kind of a linear, or not a linear, but a continuous expansion of the polymer crystal lattice. What we see with these two polymers is a bit different. So with P3-MeEMT, what we see is that there's not really much of an expansion as we drive ions into the film, so maybe only 2% or so. With Pb2-TEG, however, we see something really surprising. We see that we kind of start off with a single diffraction peak, and once we hit a certain threshold voltage, we see this huge jump in the lattice spacing, about a 27% expansion that happens over a very short voltage range. And it's also important to note that this is reversible. So if we add ions, we see this jump. If we apply a reverse bias and take ions out, we see this jump back down. And so what's going on here? And so this was with X-ray diffraction. If we turn to grazing incidence wide-angle X-ray diffraction to get 2D diffraction patterns, what we see are two completely different crystal structures in the doped versus undoped regions on either side of this discontinuity. So we have two very different crystal structures. Now, in between these two crystal structures, what we might expect is a gradual change between each two, but instead what we see is phase coexistence. And so we see that these two crystalline phases at these intermediate voltages are existent at the same time. And so we're able to solve this crystal structure. And what we found is that this polymer actually acts like a molecular zipper. And so at first the ions, the side chains, are crystallized. And as the ion enters, they kind of unzip, and then the backbone crystallizes, which can actually be seen in this diffraction peak right here. Recently, this mechanism was verified using molecular dynamics simulations in a separate study by the Zozelenko group. And they got very similar results to what we got with our GWACs. And this was really exciting. And so kind of putting this all together, we see that The backbone here between these two polymers really impacts how ions enter the film. So in P3-MEMT, we see that the diffusion of the ions is really not limited by any changes in the lattice structure. Whereas with PB2TTG, we think that this phase transition at the interface is what's restricting diffusion at the interface. And so there are a lot of open questions about this system. So one is, what's happening at these kind of intermediate length scales between the bulk and between the molecular scale. So we've started doing some measurements using nanoscale infrared imaging. And here we're just putting more and more ions into our film, and we see that some areas look like they expand, while as other areas stay about the same. And we can correlate this directly with the local ion concentration and actually map out where ions are going inside of this material. And so this is still something that we're trying to figure out exactly why we see this spatial pattern of ions, but this kind of confirms our bulk studies showing this phase-separated state. The next thing that we're really interested in doing in the future is looking at what are the design principles for these types of phase transitions. And so what happens if we take our side chains of our polymer and make them longer? Well, it turns out I'm not going to show the data here, but this actually still has this phase transition happening. Yet, if we have a random copolymer where we add these alkyl side chains, we see that we no longer see this discontinuous expansion, and we have a more P3HT-like or continuous expansion of the polymer. And so I think there are a lot of really exciting future questions to ask about these types of systems, and I hope to tell you about them in the future. But for now, I just want to acknowledge my postdoc group, in particular my advisor, David Ginger, Lucas, who I've worked with on a number of exciting projects within the group, and everyone bolded here that's part of the ion transport subgroup. Should also thank the Washington Research Foundation for their support for my postdoc, and thank you so much for watching. Please feel free to reach out to me with questions at this email, connorb@uw.edu, and thank you again.